Right, so welcome back everybody. I hope you had a nice lunch break, and we're going to carry on with our material on Singularity. And this is the session where things start to get interesting, because we are going to leverage our Docker knowledge from yesterday to help us with building Singularity images. So you'll have to bear with me as we go through this. There's a fair bit of I guess, Linux systems-y stuff that we're going to cover in these sections. Some of you may be familiar with it, others not. Obviously, the helpers are here to provide assistance, so please do ask questions. If you're struggling with anything, you're also welcome to unmute at any point and ask a question if you want to. But I think we can certainly, we've got the chat, and then we've got breakout rooms as well if there's any issues that you want to go through. So we'll see how things go and how we get on with things. And we will take breaks as we go along to give you time to catch up if there's anything where you need some time to catch up with things. So we're on episode number, I think this is episode 6 on the thing. It's actually the one that was listed as being the session before lunch. So we didn't quite get to the point that was suggested as lunch earlier, but I think we've got enough time to catch up again and keep up to time. And in fact, this is really the second part of the Singularity material, so it makes sense to do this all together at this stage. So what are we going to look at? We saw the basics of how you can work on the ARCHER2 platform to run Singularity containers and to open a shell in them, and to how to run different commands that bind to directories and so on. But we didn't actually look at how to build images. Now, again, you'll see some similarities with Docker here, but there are also some differences. So as we go along, hopefully those will become clear. Between Singularity and Docker Hub, there's obviously a huge array of images, as we said, but it's still the case that you're quite likely to want to build your own images, particularly if you're working with scientific codes and you want to set up something that's a specific configuration that you have on your local system, or a particular code that you have that you've built locally. So this is something which is hopefully very useful in getting you to the point where you can bundle up your codes to use on HPC infrastructure, and to work with particularly as we go on later, look at working with parallel codes as well, if that's something that's a use case that you have. So you worked so far in your own user account, you're a non-privileged user, but to actually build Singularity containers, you do need administrative access. So I say need, that's not entirely true, because there are ways to do it without administrative access, but it's highly recommended that you do this as the root user. There are various issues that can occur if you don't. There are actually options with Singularity to do this image building process as a non-privileged user. We're not going to cover those here. We do highlight that they exist a bit further down, but it's not covered specifically in this section of the material. There is some discussion in the linked material here. That's the Singularity user guide that talks about this, but you should bear in mind that obviously on a large HPC platform, you're not likely to have root access. In fact, you're almost certainly not going to have root access unless you're one of the system administrators. And so the benefit here is you can actually build your containers on a separate platform. So you can build your containers outside of the HPC infrastructure, where you have administrative access, on a system where you have administrative access, and then you can take those containers onto the HPC platform and run them there. We're going to look at how that process works throughout this afternoon. So there are 3 different options for accessing a suitable environment to undertake the material in this part of the course. One is to run Singularity from within a Docker container. This will enable you to have all the required privileges that you need, and the root privileges to build images. The second is installing Singularity locally on your system, where you have administrative access. So if you've got a laptop or a desktop that you're working on which you have administrative access on, you could, if it's a Linux laptop or desktop, theoretically install Singularity on there. If you're used to doing Linux system administration tasks and building code from source, whatever, this might be something that's fairly straightforward for you to do, but it's not likely to be the case if you're not familiar with that. It's likely to be a more of an advanced process. So that's something which, if you do have a Linux box, you might want to look at, but if you don't, it's not going to be an option anyway. And the third option is to use Singularity on a system where it's already pre-installed and you have root access. So if you have some sort of system that's provided by your institution, maybe you have a desktop provided by your institution, and Singularity is bundled up as part of the desktop deployment that's available there. Maybe you're in a situation where you have root access on the machine and you can do that. But again, that's something that is very site specific, and it's something that you may or may not have, but we won't focus on that here. So what we're going to look at specifically here is number one of these three options. The reason we're looking at that is because, as is already mentioned, Singularity is really a Linux only tool at the moment, and many of you will be working on other platforms, be that Mac or Windows. And so this approach of using Docker, especially following on from the course that we did yesterday on Docker, gives you the opportunity to be able to use that Docker knowledge and to run Singularity within a Docker environment, which means that you can run it on Linux, Mac, or Windows platform and have the necessary permissions to build your images. So in this episode, we're actually just doing some sort of preliminary work, some preparation to make sure that you can actually run that Docker image and that you can see how it works. And as I say, you'll have to bear with me. The command line gets a little bit unwieldy. You get lots of different options to add, but we'll look at some ways that we can make that a little bit easier to work with as we go along. So there is some information here. If you did want to, maybe you already looked through this, if this was of interest to you, to install Singularity locally on your system. You can always come back to this later if it's something you want to do once you've finished going through the course. But there's some links there that might help you with doing that. I'm guessing that most of you will have access to a system with Docker installed because of yesterday's course, so hopefully that accounts for everybody here. This material is something which is obviously available publicly online, and therefore there may be people who are working through this who are not doing this as part of a course, so that's why this information is here. It's also possible that there are cases where this will be taught not in parallel with Docker, which is why that box there is provided. And there is also a note in that box about using the fake root option if you don't have the administrative access. But as I mentioned before, that potentially there are some challenges there. We're not going to go into the detail of that here. So getting started with the Docker Singularity image, it's available from key.io. Key.io is a repository. It's a Docker image repository that is an alternative to Docker Hub. So I don't think we talked yesterday in great detail about other repositories. There are not. You can actually run your own repository. There are many sites, institutions that run their own repositories and so on. I don't think there are huge numbers of public Docker image repositories, but key.io is one. It's run, I believe, by Red Hat, the Red Hat Linux people that do the Red Hat Linux distribution, and it is something that is reasonably widely used. There are lots of images on there, and it just happens that the Docker image that's provided by the Singularity people is hosted through key.io. So what we're going to do here is just familiarize ourselves with that image and just get started with that. So if I just look at the key.io, so I'm going to open a window here in the browser to show you the key.io repository. So this is the Singularity Docker image within the key.io image repository. If you go to the little tags icon on the left-hand side here, you'll see all of the different versions of the image that are available. So you can see, as we saw yesterday with Docker, this idea of tags. So you have the image name, colon, the tag, and these are all the different tags with the different versions that are available. So 3.8.1 is the most recent version of Singularity. When the course material was originally written, we were down at 3.5.3. We're actually sticking with that for the purpose of the course at the moment. One of the reasons is that 3.5.3 is the version that's on the ARCHER platform that we're using for this course, so it makes sense to stick with something that's the same version on your local platform. But equally, you could use a newer version, and as far as I'm aware, they're compatible. There shouldn't be a major problem. But certainly, I recommend for the purpose of this course that we use 3.5.3, and specifically, we're using the slim version of the image, 3.5.3 slim. Mostly because it's much smaller, it's quicker to download, takes up less space on your system, and so that's something that that's the version that we're using. Because it's a cut down image, so the slim means that it's as you can see it's much smaller. It's 68.4 megabytes compared with the equivalent standard version, which is 368 megabytes. It's missing a number of bits and pieces that are not critical in any way to what we're doing, but you'll find things like if you want to open a shell in that in a container based on that image, there isn't a bash shell. Bash is not installed. It's got a sort of cut down environment, so you can use bin sh, so /bin/sh to give you a cut down sh shell rather than the full bash shell. These are sort of minor things. They're not big problems on what we're doing, but that's just to highlight that that's one of the differences. So we're going to be using that particular image. We are, as explained here, using the slim version of the image, and we're going to do this. This is on your local machine, or the machine where you have Docker and you have administrative access. So this is whatever you were using yesterday to give you access to Docker. I guess for most of you that will be a local laptop, or maybe you're running in a virtual machine where you've got Docker installed. But either way, that's the platform we're using here. So this particular part of the material is not being done on ARCHER2. This is being done on your local system. And what we're going to do is we're going to work with this container. We're going to create a directory in which we can bind mount into the container, so that when we create Singularity images, so Singularity image files, they can be stored in this directory, and then they'll be available on our host system when the Docker container exits. So this is very similar to what we demonstrated yesterday using the bind mount -v option with Docker. So I'm on my local machine here, so we'll just clear the terminal, give us a clean terminal to work in. I'm in a directory TMP, just a temporary directory that I've created to do this. I have a few bits and pieces in there. We won't worry about those for now. We'll come and look at those in a bit. And that's the directory I'm going to use to do my building of my images. So if you create it, so in fact, I probably should actually create a directory Singularity data to ensure that this is the same as what everybody else is doing. So let me just do that. I may even have one. If I don't, okay, I will make it. So make directory. So tilde is just a shortcut for home. So that's my home directory, and I'm going to create a directory called Singularity data. And then I can indeed use the $home that we saw in the example on the web page, Singularity data, and I'm in an empty directory. Okay, so we'll work in there for this. And what we're going to do is we're going to bind mount that when we run our Docker container using the -v switch as we showed you. There's also a few other things to note here. So we'll need to use the privilege switch to the Docker command line. This is because Singularity uses certain features that require privileged access to the host system. So it's to do with the way that it's, I believe, to do with how it's creating disk images and how it's mounting images to be able to generate the resulting CIF image file. So we need to add that privilege switch. Otherwise, if we don't, you'll get errors. Things won't work properly. And if you want to run a shell within the Docker Singularity container, as we'll see in a minute, the container is pre-configured just to run the Singularity command. So I think we saw this yesterday when we looked at the Jekyll example, where the container was configured to run Jekyll by default. This is very similar. It's configured to run Singularity by default. If you just run the container, you're basically just running the Singularity command in the container. That's fine. We're going to see how we can take advantage of that. But equally, if you did want to run a shell within the container, you would have to use the entry point switch, which I think we looked at yesterday as a -- entry point, to tell it to run bin bash, or in fact in this case it would be bin sh, because there isn't a bash shell in the slim image. That's not something that's critical here, but we can look at that. Certainly if you have a problem with that, do let me know if you want to do that, but we won't need that for the example we're going to do here. So there's now some questions or exercises to follow here, and I'll actually walk you through some of these because it's going to get a little complicated probably if you're not familiar with running these things with lots of different switches. But have a think to start with. Can you think about run how you ran a container yesterday, what you had to do with the Docker run command, and what's actually going to happen when you run the container? Then we've got this idea of running the interactive shell. There's the hint there about using the entry point switch. And then where it starts to get a little bit confusing is, can you run a Singularity shell in a Singularity container within the Docker Singularity container? So we're going through sort of two levels of indirection here. So what that means is that effectively within the Docker Singularity container, we're in a regular Docker container that's got Singularity installed. Can we use the Singularity installation in that container to then run a Singularity container within the first Docker container? It starts to get a little bit confusing, but in theory it's possible. You should be able to do that, and that's one way that you can test that your image that you've built works okay, especially if you're on a machine that doesn't have Singularity installed. There's not really any other way for you to test it locally. So that's what we're going to do in this particular episode. I will give you, there are obviously, if you expand here, you'll see the answers, and I will walk through them in detail. But I'll give you just sort of a couple of minutes to go and have a look at the key.io repository and see if you can just work out what the sort of base command would be to run the Docker container, and see if you can get to that point. So the first one of these, bearing in mind that we're going to do the bind mount of the directory. So we want to do a Docker run, we want to bind mount this home Singularity directory, Singularity data directory on our home machine, our host machine, and we want to bind it to the location home Singularity on the in the Docker container. And we also need to make sure we put in privileged when running that. So see if you can, based on what we did in Docker yesterday, make a start on that. I will give you 5 minutes. Let's restart at 5 to the hour, so 5 to 2, just to have a look at that. Feel free to ask questions, and as I say, I will walk through that in detail in a few minutes. But hopefully you'll be able to get started with that at least. So somebody's put a question in the chat, so I'm going to actually walk through this in detail now. I was actually sorry if I wasn't clear before. I was actually just expecting you to have a look at number 1 of those 3 questions and exercises at this stage. But if you have got further, that's great. But so somebody's shown that they've created an alias. In fact, I'm going to talk through that in a minute about creating a command alias. It looks to me like the command alias that you've written there, the reason why you can't find the image is because you haven't bind mounted a directory on the host machine. So what's actually happening is you're starting the Singularity Docker, you're starting the Docker container, the Docker Singularity container, and you're pulling an image, and that image is basically just being pulled into the container, and then the container exits, so then you lose it. So if you don't bind mount a directory, then you won't be able to pull the container into a location that's then accessible on the host machine when the container exits. I hope that makes sense. If you don't use the --rm with Docker run, which it looks like in that example you haven't, the container will actually just go into a stopped state. In theory, you could go back in and get it, but that's going to complicate things rather a bit. So I will show you how that works. We will look at creating an alias in a minute. So just bear with me for a minute while I do that. So I can see some people have managed to do this successfully. I'll start walking through things, and we can see how people get on. If you haven't managed to do it, don't fear. It is a little bit complicated to do this, but hopefully it will all make sense. And it's really important that we do get this working, because you all need to use this through the other parts of the building the image this afternoon. So I will close the poll for now, and then I'll put it up again in a few minutes, and we can just check that once I've gone through it, that people have managed to get to that point. So, okay, so we're trying to create trying to run the Docker container to start with. So the name of the name and tag of the image that we wanted is this. How did I know that that's what the name and tag was? Well, in this case, I went to the key.io website, and in fact, for the page for the image, and I think this is the case for all images on key.io, it tells you pull this container with the following Docker command. You can see that here, and it shows you the path for the image that you want to pull. We want to pull a specific tag, so as we saw yesterday, you can put a colon and then the tag name, and we got the tag from this list of tags. So that's where we got the 3.5.3 slim tag from. So what we actually want to do when we do our Docker run is we want to Docker run this particular container, the key.io singularity/singularity colon and then the tag. So I'll show you what that looks like in a second. And we need to bind mount the directory, as I mentioned, and then we need a few flags that we need to provide to make sure that the various features are provided. So let me go to my terminal and show you what that looks like. So let's clear the terminal again. We've got a clean terminal to work in, and we can say Docker run. I put in the -IT, which gives us an interactive terminal. We shouldn't actually need to have that, but it does mean if there was any prompts from the Singularity command, any questions that it asked, we'd actually be able to interact. If we didn't put that, there's no way to interact with the terminal, with the container when it runs. So I'm putting that in there just in case that's required. I'm putting --rm, as we saw yesterday. That basically deletes the container when it exits. It just stops us having a build-up of a huge list of stopped containers. Because actually once the container's run and done the task we've asked, we don't need it anymore. So that's why I'm using --rm. I'm going to use -v to mount the current directory. So we saw yesterday we could use this $pwd current directory, and I'm going to mount it to the location home Singularity, as was asked in the material there. And I need to put in --privileged, as we were told. So as you can see, it starts to get a little bit long after a while, the command line, and we'll see how to work around that with an alias in a minute. And I think that's everything. I then just need to provide this string for the image. So that's the image that I want to run. So I'm going to run that command. So we can see there the command is run. And what's actually happened? Well, it's run Singularity, and Singularity hasn't been given any parameters, so it says, I don't know what to do, so I'm going to give you the help for Singularity, the usage. So that's what we see there. So that means it's actually worked. It's run the Singularity command. So what have we achieved here? Well, I've got a Mac here which can't run Singularity natively, and so I don't have a Singularity installed locally, but I've been able to run the Singularity command effectively as though it was installed on my local machine by running this Docker command line. So that's what I've got now, something where I can actually run a Docker command that gives me the running of the Singularity tool locally on my machine. So that's where we've got to there. We can prove that we have an ordinary Singularity deployment because we can test using, for example, the cache list command. So if I try to run that, there's my command that I ran before. We saw it run Singularity by default. We then need to provide any parameters. So the parameters are cache list. And we can see there the cache is empty. What that's actually showing us is the cache inside the Singularity Docker container, which is just provided as an empty cache when we've downloaded the image. So that will always show us being empty unless we're actually in the container doing stuff. But otherwise, it's always going to show, because it's starting a new container every time we run the command. That new container that gets started will have an empty cache. So that shows us that is actually that's working. And so that means we've now got the ability to run Singularity on our machine. We could run an interactive shell in the container if we want to. I will show you how to do that. We don't necessarily need that, but it can be useful. So if we take that command that we ran before, we don't need the cache list anymore. So that was the command that we ran that just showed us the Singularity help. But in fact, what we can also do then is add our -- entry point. So what we're saying here is override the standard entry point in the container, which is set up to just run the Singularity command. So it's probably running like /user/bin Singularity or something like that. Override that and instead run a shell. So in this case, we're going to run bin sh because that's the shell that's available in this cut down image. So if we run that, and of course for that you will need the -it, because the -it is what gives you an interactive. -I is interactive, and t I think is tty. It gives you like a sort of terminal interface. So you need the -it if you're going to run a shell, because otherwise you won't be able to actually interact with the shell. If you don't put -it, the thing will start and you'll see the shell prompt, but you won't be able to type anything because it's not effectively connecting your terminal into the container. So let's try running that. So now you see we've got a shell, and that's actually a shell in the Docker Singularity container. And what I'll find now is I can run like Singularity, the command, and it's a bit like being on a server or something that's got Singularity installed, but with the benefit that I'm actually the root user, so I can do stuff that requires me to be root. So you can work with that, but there's as usual, it's not entirely straightforward. There's a minor issue with that, which we'll look at in a moment. So you could use that approach, but I think probably easiest to just stick with the running it from the command line each time. So I'm going to exit out of that. So running the Docker command basically for each Singularity command that you want to run. And this question about can you run a Singularity shell in a Singularity container? And the answer is yes, you can. I'm using a test image here. We haven't actually built this yet. We will do soon, but I'm just going to demonstrate it for you with the test image that I've got. So what I'm going to try and do here is I'm going to use this command to run the Docker container. So the first thing I actually need is the image that I've got here as a test. So let me just go back to the previous directory. So we had the test image there. So I'm going to copy that. My test image.cif, that's my CIF file, and I'm going to copy it into my home Singularity data directory that I was working in before. Let's go back to there. Right, so I'm in the same place as in previously, and I've got the file there. So this is the same setup that you would have. You won't have this on your machine at the moment. We'll come to that in a little while once you actually get the chance to build that. So this is just a demonstration. So what I can do now is I've got my Docker run command. As we saw before, take out the entry point. That was from the previous test that we did. We don't need that. Right, so there's the Docker run command that we had previously. If we just run it on its own, just runs the Singularity command, nothing else happens. We want to run Singularity run. So let's do Singularity run. And we need to provide some parameters to Singularity run. So in fact we're just going to provide one, which is the contain parameter. Don't worry too much about that at the minute. I can explain more about that. But actually, if you try to use this Docker Singularity container to run containers that you've built, if you don't do some other configuration, you'll get an error. But the -c works around that as a temporary, so it's much easier to just put -c for now. So so we're going to do Singularity run. So basically, this whole first part of the command is effectively equivalent to writing Singularity. And we say Singularity run -c, and then the image that we want to run. And this is the path to the image is given relative to what it is in the container. So we are mounting our local, our current working directory, the directory we're in at the moment, where that image resides, because I've just copied it into the directory. We're mounting that in the Docker Singularity container at home Singularity. So as far as Singularity is concerned within the container, that's where the location is of the image that we're running. So that means we have to tell it the location relative to that. So we say home Singularity and then the image name. So my test image, I think that was what I called it, .sif. And let's see what happens if we do that. Right, so it ran. So what we did there was we started a Docker container, and then we started a Singularity container within the Docker container, and it ran and it printed some output. So don't worry too much if that's a little confusing at the moment. There's sort of two layers of indirection. I hope it at least gives you some idea of what's possible. What that's showing you is that on a Mac or a Windows or a Linux platform where you don't have Singularity installed, you can actually run Singularity containers through this Docker Singularity container. It can be confusing, but it is very, very useful to be able to do that, and it's great if you want to be able to test things and you don't otherwise have Singularity installed. And even if you're working on Linux, if you don't want to get into the process of building Singularity from source code, this is a nice way to be able to run things. So that is basically demonstrating what's possible. There's a bit of explanation here about what the contain switch is doing. I think probably better if I go into that in a bit more detail later. We'll see a little bit more about that later. But I mean, really, I think the Docker Singularity image is not designed for running Singularity images. It's more designed for the purpose of building them, which is the main thing we're using it for. And that's why this additional configuration is required. It's not a major issue, but it is, if you just as a workaround to test things, you can use the contain switch, certainly for small scale tests like what we were just doing. So where are we up to? I think at this point it's probably worth me looking at talking about aliases. So so as we saw, typing this command that we have to type every time gets unwieldy. It's not very straightforward, and it's very easy to make mistakes because it's a great big long command with lots of switches. And so what we'd ideally like to do is to avoid that if we can. And the way we can do that in a shell, so if you're running on Mac or Linux, this will work straight away. If you're running on Windows, I'm afraid it won't work by default in a Windows shell. There are, I think, alternatives in Windows, or you can use a bash shell in Windows if you're using git bash. Some of you may have git bash installed. So there's Git for Windows, I think, it's gitforwindows.org is the website where you can download. So that gives you Git, the Git version control software, and it also gives you a bash shell. I'm pretty sure if you're on Windows, there's probably a way of doing this in PowerShell. I'm not a Windows PowerShell user, but there may be people here who are, who can tell you how to create an alias. But I'll demonstrate how to do it on Mac or Linux, and you'll see why it's useful. So what this basically means is we're creating effectively a shortcut for a command. So it's an alias to a command. So what we're going to do is replace this long command that we're having to type every time, which gets a bit messy, with something much more straightforward. So the way that we do that, and you can see on here, this is for a bash shell. The syntax is slightly different. In fact, I'm going to confuse things by that. I'm going to go into a bash shell because I'm not by default a bash shell user. We won't go into the details of that. I'm actually using TCSH, which is an alternative shell, mostly for legacy reasons, but I won't confuse things by sticking with that. I've just switched into a bash shell. It's much easier for me to demonstrate this to you that way. So this is the syntax that you use for a bash shell. So if we go across to here, and so let's just take the command. We check that we've got the right command and it works. So we run that. Yes, indeed, Singularity ran. That's great. And what we're now going to do is we're going to say alias, and we're going to create an alias which is just Singularity. And we're going to say that that is this command. So what that's doing is saying that I'm going to create effectively a new command called Singularity, and every time I type it, it's going to do the equivalent of running this long thing every time. And it just avoids us having to type that great long thing every single time. So thank you there. We got a long says that the ZSH works as well. So yeah, if you're using different, if you're using other shells, so Bash, ZSH, and I guess maybe you can do this in SH as well. I know this in C shell, so CSH, TCSH, the syntax is a little bit different. You can do it, but it's just a slightly different syntax. So we run that command. So that means now in this shell, I've actually got a command Singularity that didn't exist before. And every time I run it, it's basically the same as me having Singularity installed on my system. And what that's actually doing every time I type that command is creating a new Docker container, running the command Singularity, telling me that I haven't given it necessary commands, and it just runs and exits. So it's a much nicer way to do things. So what I can now do is, if I wanted to, I can write Singularity run -c home Singularity my test image .tif, and we're now able to run Singularity images like that. So I hope that makes sense to you. I apologize if it's a little bit confusing, but I hope that it at least is something you've been able to follow to the point of getting this to run. So before we go into more detail about building images, let me just put a quick question up to see that everybody's generally happy with that. So, so I'm going to ask if you've been able to run the Docker Singularity image, and I'm not asking whether you were able to run this test that I just did with running the test image, because you won't have got to that point yet. We haven't covered sort of the stuff, but just to check basically that you have been able to run it and see the help output is what I'm keen to know at the moment. So see where we're at with that. So we've got quite a few yeses, but also quite a few people who have not responded yet. So it's encouraging to see we don't have any no's yet. But if you do have a problem, do please let us know. You'll need to be able to use this later, and we've got people here to help who can assist if you've got a problem with that. So hopefully, I guess I should put yes myself, because it's easier to see how many people are waiting on. So we've got 5 or 6 people who haven't yet, or 5 people haven't responded, but I'm hoping. Okay, so I'll assume people are okay, but do if you do need help, put a message in the chat, and one of the helpers will be happy to help you. But that's encouraging. It looks like most people have been able to get that working and to follow with that. Okay, great. So we'll close off the poll, and we will move on, I think, from that. So you can now see how to run Singularity in an environment where you have root access using Docker. And we need that to be able to, so that was what we were going to originally cover before lunch. We'll move on to the building Singularity images, and you basically need to be able to do that to do the next stage, which is building the images. So why are we interested in this? So this is now a little bit of a kind of a bit of an aside, but hopefully this will provide you with some useful general information. So Singularity is widely used in the scientific research software community, mostly because of the fact that it's well suited to running on HPC infrastructure, as we've already talked about earlier. And so it's really built a kind of following in that space. And it provides great support for reproducibility, as does Docker. We saw this with Docker yesterday. So if you build a Singularity image for some scientific software, and this is, I think, perhaps more specific to it's the case in many different realms, but particularly in the case of scientific software, it's quite likely that you want to be able to reproduce some exact environment again. So it's often not just as simple when you're working with scientific software as just installing, a stock package or whatever, and everything's ready to go. There's often a lot of fiddling around that needs to be done in configuration, especially if you've got some very niche piece of software. And if you're writing a paper, you're publishing something where you explain how you got your results, and there's a lot of detailed process to go through to get to that point, it's increasingly the case that journals and other places where you might publish software want to see the process that's been followed, or want to have some way that it's easy to reproduce that process. So containers are really, really good for that. But it's something that's particularly, I think, important within this kind of scientific software space. And so, perhaps you've got something where you want to verify the results of something, or you want to verify the results of somebody else's work, or they want to verify stuff that you've done. But maybe you're just making a tool available to other people in the community, and you want to make sure that they have all the right versions of the dependencies and so on, which can often, as we probably all know, if you've had to try and install stuff, be a bit of a nightmare. So it's a great way to provide that support. And in the same way as Docker, we have this idea of what's kind of known generally as configuration as code. So this idea that you can produce something that is a kind of configuration file that defines the structure of your image, and it's fairly small, it's a text file, and it's very well suited to storing in standard code version control repositories. So, if you've got a resulting image that is 10 gigabytes in size or whatever, you really don't want to be putting that in a repository. It doesn't work well. These kind of large binary blobs of data do not work well in version control systems. So if you change the image, you're likely to have to store another copy every time. So to keep the history, you're going to have multiple copies. It's incredibly inefficient in terms of space, and it's not something that you would want to do. Whereas with a definition file, where you've got potentially just a small text file that describes that environment and can be used to recreate exactly the same environment again, it's a really nice way to work with providing that environment and that structure. So that's why these kind of files, these definition files, are used, and they are, as I say, very well suited to putting into version control systems, where it's very easy to store changes to the files to make sure that you keep a history of them, but you're not consuming vast quantities of space. So when you want to build a Singularity image, there are some different approaches to doing that. We're going to look at two particular approaches here, or we're going to describe two particular approaches and focus on one of them. So the options are building in what's called a sandbox. So you can build a container interactively within a sandbox environment. So what that effectively gives you is an environment a bit like you've got a sort of clean server that you might work on, so fresh install of an operating system, and you might sit in front of that machine and install all the various packages that you need and set up all the configuration, and you kind of do it as a manual process, working away at the keyboard. And you can do that, you can get everything installed, you can get yourself to the point where you've got everything working and it's usable, and then you can effectively exit the sandbox and convert it to a Singularity image. So you do all of this kind of manual work, and then you have everything configured exactly as you want it, and then you kind of drop out and say, right, store this particular thing in its current state as an image that other people can then use to create containers from. So that's one option. And the other option is then to use the Singularity definition file, as I've described above. There's various benefits to using those types of files, and this is effectively the equivalent of using a Docker file, so it's the same approach. And that's what we're going to focus on here. And really, to reiterate that point above about reproducibility and related aspects, the reason that we're focusing particularly on that, so in fact there's a question here that asks why do you think we might be looking at the definition file. I don't know if anybody would like to have a suggestion why that might be before I go and explain it. If you've got the thought, please do put something in the chat. Just give it a moment in case anybody is typing something. Yeah, so we've got a suggestion that somebody else can see what the setup is easily. That's absolutely true. Any other thoughts on that? Yeah, easy to change. That's also something that's a benefit of using those files. Yeah, so I think we're definitely on the right track here, and these are all kind of perfectly valid points and very good points. So I think the thing really to highlight here is that the definition file gives you a much kind of cleaner set of commands. We all know that when you try to do stuff, even when you think you know how to install something, it never goes quite. If you sit down at a keyboard and start installing something, you invariably forget the steps that you've done somewhere along the way. So I've had numerous experiences of trying to get something working. It all seems pretty straightforward. Then you run it and it fails, and you realize, oh, I forgot to edit this particular configuration file or set this value. So you go back and you edit the configuration file and you set the value. And then you run it, and then something else didn't work because you had the wrong version of some dependency that you installed, so you have to go back and find what that is and install. And you kind of go through this process, and if it's sufficiently complicated, you actually forget most of, you know, the things that you had problems with. And although the thing that you've got at the end is it works, so you can bundle it up in an image, it's great. But if you then need to do it again, or you need to do something slightly different but based on the same sort of base structure, it's incredibly difficult to remember exactly what you did. Even when you note it down, there's often things that you forget or something changes in the system or whatever. So really the main reason for this is the kind of the straightforward, explicit nature of how you specify the steps. And it makes it very, very clear everything that has to be done and the order that it has to be done. And exactly as stated there, somebody else can then see what the setup is, which is great. But it also means that the setup is done in a way that makes it much clearer to work with for yourself in the future, and also and you know, as stated there, it's also easy to change. You can make changes to it, and it's very clear what's actually happening. So that's why we focus on that approach here, and it's something that you know, I think is very useful if you want to produce containers, particularly for focusing on things like reproducibility, and if you want to publish software, particularly relating to papers and publications and things. This is a really good way to manage that. So that's effectively what is covered in there. So I think we'll now look at actually creating a definition file, and we'll go through the process of looking at what's in that file and kind of how it, you know, what it looks like and what the various different things mean. So as I've stated already, it's a simple text file, and it has in it a number of statements. Now, we saw with the Docker file yesterday that there's a kind of syntax that you have to use, and there's some kind of fixed commands that you use, and the case is very much the same here. It's just the structure is a little bit different. It's specific to Singularity, and the definition file that we're going to create here is something which will just do a simple, print some simple output, but it will give you an idea of the kind of steps that you have to follow and different stages that are followed in the process. So here is an example of a simple definition file. So what I'll do is, and so what you can do at this stage is actually you can take a copy of that content. You might find that it doesn't copy and paste nicely if there are funny characters. It looks like it's probably okay actually. Sometimes you get some control characters or the quotes don't come out right, but I think it's probably okay. So what you could do is take that content and put it into, so in your Singularity data directory that we created before. We've just got a question there about what's happening when Singularity pull. Okay, so that's a really good question. So what does Singularity do to pull a Docker image? Does it translate the Docker file, or does it start from the environment itself? So in fact, when Singularity is pulling a Docker image from Docker Hub, as I understand it, in Docker Hub, it's actually the image is in a built image state. So while there may be a Docker file behind that defines the stages to build it, what you've actually got in Docker Hub is the built image. So you've got these layers. So there's just a bunch of files that are the layers within the image. So what Singularity is actually doing when you pull a Docker image, as we looked at before the lunch break, what you're doing is you're pulling these layers of the, so you're pulling the actual file. So you're not actually taking a Docker file. You're taking something which is the result of building the image from the Docker file, and you're pulling down those files, and then you're converting them into a CIF image file. So it brings down the layers from the Docker image, and then it kind of combines them together, sort of squashes them together, as it were, into a single CIF file, which has the combination of all those layers together in one file, and that's effectively what you're doing there. So I hope that makes sense. Okay, so we've got our directory, our Singularity data directory. So hopefully you've also got a home Singularity data directory. And I have my test CIF image. I'm going to actually remove that. So let's start again from scratch. So we'll delete that image. Hopefully this will work, and then I'll have it back again, but we will find out. So I'm going to now create a new file. I'm going to use VI, but you can use whatever editor if you prefer Nano or something like that, just to create a file. So I'm going to use VI, and I'm going to create a file which is called mytestimage.def. So def means it's a Singularity definition file. That's the extension that we use for Singularity definition files, and I'm going to paste in the content of that that definition file that we saw on the web page. So I'm going to save that. I've now got that one file there, my test image.def. So let's have a look at what that's actually doing. So if we go back to the web page here, so there's a number of different sections that we can see here that begin with these percentage signs. These are used to specify different sections of the build process and different configuration. There's a number of different directives that are used beginning with the percentage, but in fact we're only going to use two of them here. So this is a very, very simple example, and we're just using the post and the run script options. So let's kind of walk through this and see what's actually happening. So at the top you can see there is this Bootstrap Docker and then from Ubuntu 20.04. So what this is actually telling us is we're going to start, as we did with Docker, we think it was from that we used in Docker, the sort of capital from, and then you say which image you're building it from. Here, it's very similar. We're starting from a base image that comes from somewhere, and we're then going to do stuff with that base image to change it into the setup that we want. In this case, we're going to install some stuff in the image and so on. So what this tells us is we're bootstrapping from something which is a type of image of type Docker. So that means that the image is going to come from effectively from Docker Hub. There would be the alternative option would be to use something like S Hub, Singularity Hub. There's a bunch of different options that you could use there, but we specify Docker here, and then we say, okay, given that it's a Docker image, where is it? What image is it coming from? The base image, and it's the Docker image Ubuntu with the tag 20.04. So that's standard Docker format for the image and the tag. So that's the image that we're starting from, and it's just this Ubuntu 20.04 is just a minimal image that's provided, so it's quite a small image that we use as our base image. And I guess this demonstrates really that there's quite a lot of flexibility here, because we're obviously working with Singularity, but there's no reason why we can't take a Docker image and then use that as our basis. So that gives us access to this huge ecosystem of Docker images that's out there. So there's really a lot of flexibility in how we work with things. So this particular starting section tells us that we're going to effectively we're pulling an image from Docker Hub, so the Bootstrap Docker is the same as effectively using Docker :/ that we used before, and it's going to pull that image and it's going to do some stuff that we tell it to do with that image to give us our resulting Singularity image. So next in the file we have this post section, so %post, and what this section is doing things like once we've got the image from Docker Hub, it's going to allow us to do configuration and installation within the image. So the post section is where we do stuff that involves configuring and installing stuff in the image once it's been kind of pulled down and created, and we can start doing stuff inside it. So the commands that appear in this section are standard shell commands that you might type in a terminal on a system, and they're being run within the context of this image that we're generating. So we've pulled down stuff from Docker Hub. We've effectively created a Singularity container, and we're then doing stuff in that container. And what's going to happen at the end is then that's going to be bundled up into this image that we're going to have available. So that's effectively what's happening here. We can think of it in that context. So we use the Ubuntu package manager here. So this is the apt-get package manager, and we do a couple of different things. If you're familiar with Linux, this might seem very familiar to you. If you're not, I think we looked at some examples similar to this yesterday, but if you're not familiar with Linux, it may be a little bit less obvious what's happening. But what this is doing is it's saying update the list of packages. So what will happen when that gets run is that the system, so the package management system, goes off to some central package repository that's run by Ubuntu or a mirror that's run by somebody else, and it says, tell me about all the new packages. So it just updates its kind of database of what packages are available. You need to do that reasonably often because the packages change quite frequently. There's so many packages in the repository that there's often new ones being put in, new versions, fixes, security fixes, whatever they get put in there. So it's pretty standard to do that. So we say update. The -y means that it doesn't provide any prompts. So we want all this to be automated. We don't want it to keep popping stuff up asking us to do things, because of course you may well want to do this in an automated manner somewhere. So the -y just means it won't ask us any questions. It just accepts any prompts and says yes by default. So we update the package directory, and then we say install package Python 3. So it's pretty simple. It's going to go off and find a package Python 3, and that may well have some dependencies. In fact, I'm sure it does. And those all get the apt-get package management system handles all that for us. So it goes off and finds the Python 3 package, finds any other dependencies that are required to make that work, and it pulls them all down and it installs them. So that's what that command there is going to do. And then we have this run script option. So what this does is, this is the default thing that gets run when you say Singularity run. So this morning we saw that example with the raw.sh file that was in the image, and that was running in the hello world image. What effectively was done there was, when the hello world image was built, there was a run script section that said /bin/sh/raw.sh, whatever it was that we saw. So we looked at that by using Singularity inspect. If you recall, we did Singularity inspect -r, and we specified the name of the image, and it showed us the thing that would run by default, and that's effectively what we're specifying here. So if you did Singularity inspect -r on this image once it's built, you will see the contents of the run script section effectively. So that's what that's actually doing there. Okay, so that's our simple definition file, and we can now actually use that to build an image. So as we saw, I have my my test image definition file. Let's just go back to the terminal. So we've got it there. We can see the content of it. Now, if you remember from before, we set up the alias Singularity, or I set up that alias myself. If you're not using that, you'll have to type the long command line. The other thing also to bear in mind is that if you have just typed that into this terminal, the alias, it will only exist within the context of this terminal, this shell session. So if you close that terminal, open a new one, you'll have to type it again. There are ways to persist it. So if you're using a Linux or a Mac machine, depending on what shell you're using, there are kind of standard shell configuration files, profiles, that you can put that command into, and every time you open a new shell, it's there. But equally, so if I just type alias, I want to see what so there's the, if you just type alias, it shows you all the aliases. But for those of you who don't have the alias set up, I will use the full command, just maybe to make it a little bit clearer what we're actually doing. So that's the command that was being run by the alias. And what we're going to do is we're going to build an image based on this, this definition file. So just as a reminder, what's happening here. So we're creating this Docker container based on the Docker Singularity image, and we're bind mounting the current directory, which contains mytestimage.def, to the location home Singularity inside the container. So there's going to be a directory home Singularity in the container, and it will contain this file because it's being bind mounted to that location. And so we're going to do a build. So if you look on the command here, where this just says Singularity, that's basically the long command that I'm going to type. In fact, there's a version of it there to show you. And we're going to do build, and then the command here. I think there's a question there. Sorry, let me just check. So there's a question, is there a way to define the home of the Singularity container as part of what's put in the alias command, so that you don't need to type home Singularity every time you refer to a file? That's a very good question. I'm not entirely sure. I think that by default, so Singularity obviously does tend to mount your home directory by default. So in that case, you could possibly just put files in your home directory and use $home, or put them in a subdirectory of your home directory and use $home slash the file name. I'd have to try that and see, but that is a good question. And, yeah, Andy, go ahead.
I'm not sure it matters, because it's going to be the same every time, because you're bind mounting PWD to home Singularity. So it's static because it's the name of the bind mount, isn't
it? Sorry, say again. When the home sorry.
So the home Singularity is defined as the place you're bind mounting PWD into. So home Singularity is never going to change, no matter where you use it. It's a static thing, so it doesn't need to be dynamically changed. You see what I mean?
Right. Okay. Yeah. Okay, that makes sense. Yes. So that is true. So you could hard code it effectively to point to that location. Yeah, but there's also a point in the chat. Somebody suggested using the workdir setting, so that may well be something that that you could use to put them into the current directory within the container. That might actually be a nice way to do it. Yeah, and we'll stick with this for now as the way of doing it. Yeah, but yes, that might be something that you can look at. So we'll look at the work dir option as well as an option. That's not something that I normally use, so I'll have to double check. But thank you for that suggestion. Okay, so for now we're working with this home singularity, but there are definitely some other ways to do that. So what are we trying to do? We're going to do a build. So we're saying build, so singularity, so this is effectively the same as typing singularity and then build, and the output file, so you have to give it the order of the output file first. So the output file I want to be placed into home singularity my test image.sif, so that's the resulting file, and the input file is going to be home singularity, if I type it correctly. Whoops. No, we're still not getting there. Try again, that looks better. And my test image.def. So build an image file with this name stored into this location, which will end up in our current directory, and build it from this definition file. So you should be able to do that and hit enter. And we then see a message that tells us it's starting the build. And now we can see what's happening. So what's actually going on here is this is now pulling the Docker image from Docker Hub. That was the bit at the top. It's now running the post section of the image. So we pulled the Docker image, and that was our sort of base to start from. Then we ran the stuff in the %post section. So we ran apt get update. So there it is, pulling all of the new directory, package directory information from the remote package repository at archive.ubuntu.com. And then it said apt get install Python. So it tells us that it's going to install Python, and it shows us a bunch of packages that it's installing. In fact, it's installed Python 2.7, which was not quite what I was hoping. I was hoping for it to install Python 3. That might be me not typing the right thing. And either way, it's gone through and it's done the install. We can see all of the different packages that have been installed there, and it unpacks them all and does a bunch of stuff. And at the end of all that, it tells us it's adding the run script. So that was the thing in the %run script section. And then it says it's creating the CIF file. And finally, the build is completed. The Docker container has exited, and it's left in the current directory on my main system, my test image.sif file. So the image has now been built. Let me just double check that I didn't make a mistake by running Python 3. So in fact, this is interesting. This is not likely to work. I'm not quite sure. Something might well have changed. I think they've changed the package naming in the configuration. So it's interesting that I wonder if I actually did I have a mistake in my. Okay, this is entirely my fault. There's an error. Apologies. There's actually an error in the version there. The 3 seems to have been missing. So if you copied and pasted this one, you've probably ended up with Python 2.7. So let's. I'm going to rebuild. Let's just do that. So what we can do is we can edit the mytestimage.def, and we can change this to say Python 3. So I didn't spot that was going to be a problem before. So what will happen here is that. In fact, since the run script says Python, so I think we've changed. Let's just sorry, things here. So in fact, the run script. So this original version will actually work. It's all Python 2 specific. So here we can see that it said install Python, and what actually happened was it installed Python 2. So for anybody who's not a Python user, Python 2 or 2.7, which was the last version of Python 2, was around for a very, very long time, and it finally came to sort of end of life state. I think it was the start of 2020, might have been 2021, but it was in the last year or so. It's come to the sort of end of life state, and it's now not recommended to use that. You should be using Python 3 instead. On some systems, if you just install the Python package, it will install Python 3. But on Ubuntu, it seems that it's installing Python 2 by default there, and the Python 3 package is actually called Python 3. So in this case, it will work with Python 2. It's installed it, and then the Python command will try and run this. So let's actually just run that and show you. So there's my test image that I've got. So if I now run, we saw before, so Docker run. Let's go and click back. So instead of doing a build, we're going to do a run. We need the -c. So Singularity run -c, the image that we just built. And indeed, it runs and it gives us some output. Now, if we wanted to see what version of Python was actually running there, what we could do is run that command again. But instead of doing Singularity run, let's do Singularity exec. And there's the image that we're running. And let's do Python ---- version. And sure enough, we can see that it's run the Python ---- version command in the container, and it's installed Python 2.7.18, which is the last version of Python 2.7. So it's worked and it's given us that version. But of course, if we wanted the newer version, we can edit our definition file. So let's have a look. Edit the definition file, and let's just change it to be Python 3. So, and then run the Python 3 command. Again, many systems, it's the default Python. You just type Python, it'll be Python 3. I have a feeling on Ubuntu we need to type Python 3, which is why I've changed that there. And let's do a rebuild. And what will be interesting to see is, in fact, it won't cache the stuff because we're running in the container. So we'll just do a So I'm going to go up through my history and just rerun the command again. So we're now back to the build command. So build something called mytestimage.sif. Let's call it mytestimage i3 so it doesn't overwrite the other one. And the definition file is the same because I edited the definition file, and let's run that. So it's going to run through the same process again. It pulls down the Docker container, and then it goes off and updates its package database and installs the Python 3 package. And what we'll see this time is that it's gone flying through, and we can actually see that it's been doing Python 3. So we go up to here. Where is the package install? Somewhere up here we go. We can see now that it says the following new packages will be installed, and somewhere in that list of packages it's installing Python 3.8. So that's doing the right version this time. The thing has run, it's completed. So let's now run our Python version command again. So there we have the command that we ran. So Singularity exec -c, Singularity mytestimage pi3, that's the new image we just created, and then run the Python 3 version command. And we then see that it's now Python 3.8 content. So what we've done there is we've actually created two images. One's got Python 2 in it, one's got Python 3 in it, and we've been able to run those and prove, and we're actually running those through the local container, Docker container on the local system. So hopefully you've managed to get to that point. Let me just go back down to here. So there's the run process. So let's just see who's managed to get there and whether there's any issues so far. So maybe some people are finding it a little bit slower. Right, so there's a question about the cache. So what's happening here is because we're using the Docker image, the Docker Singularity image, and we're creating a new Docker Singularity image instance for every time we run the command, the cache is effectively not being used because the cache is within the cache within the image is empty. And so what's happening is we're running a new image. So what happens? We spawn we create an image, create a container from the image. We do something which populates the cache, and then we close it all down and we lose all the content that was in the cache. So it's a little bit inefficient, but basically that's why it's not using the cache, because every time you run the command, it's creating a new container every time which has a clean state. So the cache is not actually there. I hope that makes sense. Yeah, so okay. So let's just go. So we're on this part here. So somebody else see the last run command? Yes, sorry about that. Let me put the. It helps if I click in the right window. So is that would be when you said the last run command? You want to see this exact command that I did? Yeah. So of course, because I've got the alias there that I've got set up. So just to prove that is got the alias there. So if I run that particular alias, sorry, if I run using that alias as well, just to show you that it's effectively the same command. It's just a much simpler command on the command line. It's basically the same as saying singularity exec -c home singularity I test image pi3 sif, and then the command we want to run is Python 3 -- version. Yeah, that all looks okay. And the other thing we could do, of course, is we could just run Python 3, and we should get a Python 3 interactive shell, which we do. So, and we're now in Python, and we can do whatever. The same thing I did this morning for the demo. Just run, print pi whatever. So that's basically getting something started. Whoops, exit properly. There we go. Okay. So yeah, so the point that there's a question there about the error with etc. local time. So this is a bit of a nuisance with this container. What's actually happening is that the container that we're using doesn't have a time zone configuration in it, and the running of Singularity. When you run Singularity, we talked this morning about how it mounts certain directories by default. So this is a slight digression, but just in case people are sort of curious to know what's going on here. So we looked at how it mounts by default certain files and directories from the host system into the container. And what's happening here is that one of the things it's trying to mount is a file called etc. local time, which provides details of the time zone. And within the container, within the Docker Singularity container, that's not present. Now, I think it could be because we're using the Slim container. It might be that if you use the standard one, you don't have that problem. But with the Slim container, so I can actually show you that. So let's go back to let's Docker run. Let's type this all out again. So we're going to run this, and we're going to run the thing. So one thing I always get wrong is the key.io. Let's just copy and paste that because I'll get confused otherwise. If you've got a fast network, you don't have a problem with downloading sort of 300 megabytes. You could try using the non-Slim container and see if that works. It might actually work. In fact, I can probably try that. So I'll just show you this first, and then I'll have a quick look at that. So so if we run this particular container, and we're going to run I'm going to do a shell in it, and you'll see that equals bmsh. We've got a shell there. We've got a container in home Singularity. So if I try to just run that using Singularity run, right, we get this error that says container creation failed, mount local, etc. So what that's trying to do is it's trying to bind mount the file etc. local time, which tells you the local time zone on of the system, into the running Singularity container when it creates it. And it can't do that because the file isn't there. Now the workaround in this particular container is you have to install the time zone package and then put the file there. So I have to go apk add tz data. What that's doing, so apk is basically the equivalent in this image. What are we actually running in this image? It's so this is the Docker Singularity image is running Alpine Linux, which is a sort of cut down Linux distribution. So it doesn't use apt-get, it uses apk instead. So we say apk add time zone data, and this is not something you need to do. It's just to sort of demonstrate to you. It's just a bit of a slight sort of annoyance, and that's why we're using the -c. So if you run the command and you get this error, what -c is doing is basically saying don't mount these default. It stands for contain. It basically makes the container sort of more self-contained. It doesn't mount a bunch of default stuff from the host system into the container, and that's why you don't get the error anymore, because it's not trying to mount that file. But if you want to fix it, there is some. This is in the content here. I think it might actually be in this section at the bottom. Let's just have a look. It's probably down the bottom. It's certainly in one of the sections. It might be in the I think is it down here? Here we go. Yeah, so it's down there towards the bottom of this section if you want to see how to do that. But basically, what we're doing is we're installing the time zone package, and then we copy the file from the time zone package to the file etc. local time. Thing zone info. So, so there's a question there about why is the TZ data so important. So I think all that's happening here is that this is so that when you do stuff in the Singularity container, it knows which time zone to print times in. I suspect that's what that file is doing. So the kernel itself, or the system knows what the time is, but it doesn't know what time zone is relevant. And of course, with I guess with file times and things like that, it's rather important that it knows what the local time is. So basically, what this is doing is just ensuring that it knows not what the sort of absolute UTC time is, but what the actual local time zone is, so that everything is kind of correct in terms of timings. So I may be wrong there, but I suspect that's probably what's going on. So if I just show you, if I just copy that file, right? So now we have, whoops, use the right command. Now we have file etc. local time, and now we can actually run the image, and it will run as normal without any problems because the file is there. But it just, from what we were doing before, it was easier for the demonstration purposes to use -c to contain it. Okay, so hopefully that's given you a bit of time for anybody who is still working on this to catch up. Let's just check here where we are in terms of. Let's just put a little question up here to check. So this is just to check if you've managed to build and run the container. Looking good so far. Okay, it's looking good. So while people are just responding to that, there's just a few things to point out here. So if you're running on Linux, nobody's actually raised this. So I'm hoping nobody's actually encountered this problem. But if you are running on Linux, certainly in the past we've seen issues with the file permissions. So when you create the image and the image ends up on your local system, it ends up being owned by root, which means you have problems being able to access the file and so on. So there's a little bit of information there in case you encounter that situation to try and help you work around that. I'm hoping nobody's actually encountered that, or if you have, maybe if you already saw this and put it in, that's fantastic. But equally, if you are having a problem, that's one thing to look at. On Mac and Windows, that shouldn't be a problem because I think Docker Desktop manages all of this stuff for you. The other thing to look at there, I think we looked, well, in fact we've already gone through various bits and pieces here. No, I think that's all okay for that section. So it's good to see that many people, in fact certainly majority of people, seem to have got that going. Nobody has said no at the moment, so I'm hoping that people are generally okay with that. But if you are stuck, then do ask somebody. So just to kind of finish out this particular episode, what we're going to now try and do is actually run this on ARCHER2. So we've created this image, we've tested it locally, we can see it runs, and we now want to move it to ARCHER2. So what we are going to do is use secure copy to move the file to the other system. There are many different ways that you might want to do this. So there's lots of different approaches that you can use here. The way that I'm showing you to do it here is to use secure copy. If you're not familiar with doing copying using secure copy on the command line, then it might. I've just realised there's actually an error in this. My apologies. That actually should say SCP. So I will fix that. I'm not quite sure why it ends up saying SSH, but I will ensure that is fixed in the break. But so that should be SCP, not SSH there. But that's the approach that I recommend to copy the file across. If you're running on Windows, there are graphical tools that you can use. So there's a thing called WinSCP, I think, is quite a nice sort of simple graphical SCP client in Windows that you could potentially use. And you just put in your credentials and various details and your key and so on, and it will make the connection to the remote system for you. But if you're happy working on the command line, you can use SCP on the command line. And I think that if you're running on Windows 10, I think it's probably got an SCP client built into the terminal, so you probably should find you can just do SCP straight away. But if you can't, then you might want to look at WinSCP. But we got some questions in the chat there. I don't know if there's an issue. Okay. So yeah, so there was an issue with running the second. So it looks like, yeah, it looks like maybe you missed the home singularity on the path to run there. So it may be that it's just not finding the image because the path is not there. Also, there was an issue about failed to unshare root file system. That's not something that I have seen, I don't think. When did that occur? When you were? Is that something that's already been discussed further up? Let me have a look. I don't know. Did that error occur when you tried to, which command did you run where you got the failed to unshare root file system? For those of you that have managed to build this, if you would like to have a go at SCPing your file over to ARCHER2, then we can do a quick test and see if we can get it running there, and then we will break for a few minutes, and then we will come back to look at the next stage, which is going to be running MPI jobs. So I'll just go through this sort of end material, and I think we're then onto MPI after the break. Oh yes, we are. So yeah, so if you want to have
Jeremy,
a go at
just to know,
yeah.
Jeremy, just know
Yeah.
there's an error in the SCP command. It says SSH.
I just
SCP.
pointed that out. This one here, it should say SCP, yeah.
Yeah.
Or is there another error further on?
No, that's the one.
Right. Okay. Yeah. Thank you. Sorry, I did point that out, but just yeah. Thank you for highlighting that again. Yes, it should say SCP rather than SSH, and I apologize for that. So let me just actually, yeah. Okay, I'll fix that in the break. So yeah. So what I'll do is I'll give you a demonstration of doing that from my machine, and you can see whether you can get the same to work. So what I'm going to do here is I'm going to, let me exit out of this Docker container. So here's my image file. We'll do the Python 3 one, I think. So I'm going to say scp -i. In fact, I don't have to do the -i. I'll do it on here for this. I don't have to do it, I don't think, on mine because I've got it pre-set up. So in fact, probably might not work otherwise. Okay, I'll do it without, but you'll have to do with yours -i. And then you'll have to put the path, so it'll be something like home/whatever ID _ ARCHER2 or whatever it is. But I'm going to leave that out on mine because I've got it pre-configured. So we're going to say scp. I'm going to say the file I want to copy, which is my test image pi3. Where I want to copy it to. So my username on ARCHER2, and then now what you will have to type is login at login.archer2.ac.uk. Because I've got mine set up in my SSH configuration, I can just type ARCHER2, which is how and it will find the key and everything because I've got an entry in there for that. And where do I want to copy it to? So in fact, if you just leave it with the colon, it will go by default to your home directory. So rather than having to type /home, whatever, and I can't even remember I think it's got the name twice on the home directory, but rather than having to worry about getting the home directory right, just do the colon. So if I do that, it asks me to enter my password. May or may not have typed correctly. Probably not by the looks of things. Okay, let me try again. Right, so that was correct, and it's now asking me for the password to the key, which I can now type in. And what you'll now see is off it goes uploading the image. And again, it depends on your network speed whether it's going to how quickly it will upload. But this is now uploading the image to ARCHER2, and I don't know if I've still got my terminal on ARCHER2 here. Let's just have a look. No, I haven't. It's dropped out, so I'll just open that again. While it's copying. Been very successful with my typing today. I've got my ARCHER2. Right, so the file's copied. So that was my file copy. It's now moved across. So if I now go to my ARCHER2 terminal, we do an ls, we can see there's the image that I've just copied. So it's now on that platform. And we can now run it, and we know that Singularity exists on ARCHER2 standard. We don't have to go through all the business of the Docker containers and whatever. It's just there and pre-installed, and we can say Singularity run my test image pi3.sif, and sure enough, it runs. We get the warning that we get every time we run stuff here, and we get the output. And what we can also do to demonstrate, like we did last time, Singularity exec, and we can say the image name, we can say what we want to run. So let's run Python minus version. Oops, Python 3 I should have put, not Python minus version. And there we see that it's Python 3.8.10. And in fact, what we saw here was I typed Python and the command Python doesn't exist, so it's just giving me a command error saying the command was not found. Right, so what we've done here is we basically got to the point where we have created an image, albeit a very simple one. We've created a definition file to describe our image. We then built the image. We've verified that we can run it locally on a platform that doesn't natively support Singularity, but we've done it through the Singularity Docker image. And then we've moved that image off to an HPC platform and shown that we can then run the image there. So this is quite a nice kind of pipeline that takes you through from the kind of process of starting completely from scratch to being able to build an image of your own kind of configuration, and then to test it locally, and then to move it over to an HPC platform and to run it there. Now, obviously, this is a very simplistic example, but hopefully that gives you a kind of idea of how all this works. And I hope that many of you have managed to get to that point. I know that there are some people having some minor issues, but certainly can have a look at that in the break. But I think that's probably a good time to take a kind of 10 or 15-minute break. I think maybe we'll do a 15-minute break, and then we'll go on to we'll just look at very briefly at these closing comments of this section, and then move on to the MPI stuff in the next episode. So we will restart. So it's 3 o'clock now. We will restart at 3:15, and in the meantime, if anybody's got questions, please do feel free to ask questions, and we will try and assist. Okay, so in the previous bit of material just before the break, we went through how to build an image and how to move it onto the ARCHER2 platform and to test that it ran. So I hope most of you, and it looks like pretty much everybody's got that working. I know one or two people had some issues that hopefully we've now managed to solve, or fixes in process. So at the end of this section, we've got a very simple image that we've built, but there's obviously things can get a lot more complicated than this. So I thought I'd just make a few comments about other more advanced aspects of building images before we come on to look at the MPI side of things. So more advanced definition files, we looked at the different % directives that you can put into the using the post and the run script options. There's a number of other options that you can use. There's the % setup, % files, % environment, etc. listed here. They're all useful in various different circumstances, and we will see some of them in the next section of the material. But there's a lot of some detailed documentation on these things. There's links there to the documentation. So if you are interested in building Singularity definition files, it's worth going to look at that documentation and find out a bit more about what these different options provide. In terms of additional features, Singularity also provides a lot of other different features, and just a couple of them I was highlighting here. Again, there's really quite detailed documentation that will help you. There's linked there to the user guide. The link to the user guide there is actually to the 3.5 user guide, because that's the version that we've been focusing on here, but you will find links there to the more recent stuff. But I think the core features, certainly the things that are being mentioned here, are still relevant, and that you'll find the details of those in the more recent user guide as well. But a couple of things that I wanted to point out. One of them is the remote builder option. So if you are having problems getting things to build through the Docker Singularity container, or you find it's kind of too convoluted, or you have issues on a particular platform, one of the things you can do is to use their kind of cloud-based remote builder. What this basically means is that you upload your definition file into the service, and it will go off and build the image for you. And I believe it then actually makes the image available through Singularity Hub. So you can actually then pull the image using Singularity pull straight from the Singularity Hub. So that's one way to build images that doesn't rely on your local system. It's quite a nice system to use. I think you can basically just go and register. I don't know what the details are in terms of whether there's limits on how much you can build and whether there's sort of pricing model when you go above that, but certainly there's details with the link there. You can find all of the information about that. And The other thing that you may want to be interested in, particularly if you're working in certain domains where you need to make sure that containers or data that's in the containers has not been tampered with or changed in any way, you can sign containers. So that's just something that I thought would be useful to point out. So there's ways to ensure that the containers have some sort of signature on them that allows you to verify that the container has not been changed or become corrupted or whatever. So there's details on that as well. So those are kind of a couple of interesting features, but there's a lot more there that you may want to look at if you are interested to kind of go further with Singularity beyond what we're looking at here. Okay, so that kind of rounds out this particular episode, and that moves us on to the final episode on running MPI parallel jobs. Now, this is perhaps, I suppose, a slightly niche element, but and that's why I mean, there's quite a bit of material here. We're going to devote the last kind of 35-40 minutes to this. It's something which some of you, I guess, maybe of great interest to some people, but other people may not have specific use cases that that work with this. But particularly because we're working on an HPC platform that supports running large parallel jobs, this is a nice way to demonstrate the kind of opportunities that there are with Singularity to run parallel codes and to package up the codes in a certain way and so on. Now, what I'll do here is give you a little bit of introduction to what we're kind of specifically talking about doing here and what we mean when we talk about MPI and so on, and then we'll look at actually doing sort of building an image and running it. When we come to actually building the image, the build process can be a little bit time consuming. So we have got a test image that you can use to try this out yourself. I will build it on my local machine. It takes about 5 to 10 minutes, but I know it depends on the performance of your machine. It may take a lot longer. But we will see, and if you find that you're kind of getting bogged down with building the image and it's taking too long, there is a kind of one that we made earlier, as it were, sitting on the platform that you can work with if you want to actually just test doing the run. So MPI, what are we talking about when we say MPI? It's message passing interface. Some of you may be familiar with that. It's a widely used standard for parallel programming, and it's used for exchanging messages between different processes in a parallel application. So most applications that we run, they might be single-threaded or they're multi-threaded, but they run within the context of a single node or a single system. And effectively their threads and the different elements of the application get managed by a single instance of an operating system that's running on that single node. So where you've got multi-core processors, then the operating system can schedule your threads potentially onto different cores so that you've got multiple threads running at once. But if you want to go beyond a single node, it gets a lot more complicated. So you need some way, if you go beyond a single node, to run parts of your application, as it were, on each node, and for those different parts of the application to be able to communicate with each other. And the way that works, I say be able to communicate with each other, there are different types of parallel jobs. Some communication between different elements is not actually an important part of the way that the code works, but there are many where it is very important that different parts of the application can communicate and share information to do the sorts of calculations and processes where they can't be done, where different elements of the process can't be done in isolation, and they need to actually be aware of the other parts of the application. So one of the ways that we handle that is to use this library's MPI, message passing interface approach, and there are a number of different implementations of MPI that can be used, and very, very commonly this is found on large clusters. The MPI libraries are deployed on large clusters, and one of the sort of really common ways that people use to run different parallel codes on these large platforms. So with Singularity, we've seen that we can we have trouble building without root access, and we specifically focused on using the Docker Singularity container. And because we're not likely to have root access, as I highlighted before, on these large institutional or regional national clusters, building a container directly on the target platform is not normally an option. Now, what normally happens with codes on sort of large parallel codes that you might want to run on HPC infrastructures is that the developers or the people that want to run them have to get the source code, and they download the code onto the specific platform where they're going to run it, and they build the code specifically on that platform. And the reason for that, the reasons are manifold, but one particular core reason is that these kind of big parallel platforms often have specialist hardware and associated software that provide the linking between the different nodes in the cluster, and you often need to build your code against the implementation that's on that actual platform in order for it to work efficiently. So that's the reason that you often need to build your code specifically on the platform where you want to run it. Now, there are two kind of widely used open source implementations of MPI. One is OpenMPI, and the other is MPitch. And I've got links to both of those here in the material. And if you have a platform that's working with OpenMPI, there are some cluster platforms that provide support for OpenMPI, but it's often the case that large cluster platforms have some sort of commercial implementation of MPI on them, which you can't just go and download and run on your local machine to build the code. So you won't be able to build using the exact implementation that is on the cluster that you're building on if you want to build a Singularity container on another platform. So if you want to build on your local machine, as we just saw in the example that we looked at earlier, and then you want to move it to the cluster, if you want to be able to build an MPI code, you are not likely to be able to build using the MPI implementation that's on the cluster itself, because you probably can't access that or can't download and install it if it's not an open source, freely available implementation. Now with MPitch, there is compatibility. There is this ABI compatibility, which is basically the binary interface is compatible across different implementations. And many commercial implementations of MPI have this compatibility with the open source MPitch implementation. So at this link here, you'll see that there is a list of the different compatibility versions. So here's some details. This is, I think, perhaps a little out of date, but it's probably still correct. And so you can see there's some different versions that have binary compatibility. And so what that means is that you can build a Singularity container with a code that requires MPI, and you can build it against MPitch, the open source MPI implementation, in your Singularity container. And then you can move that Singularity container onto an HPC platform, and it will work there. Because there is compatibility, the MPI version that's in the container and the MPI version that's on the cluster that you're running on. So that's a real benefit for being able to build Singularity containers and making them somewhat portable, which is often a big challenge with sort of complex parallel codes. So when we build on our local system, as I've said, and we use this compatible version, MPitch in this case, of MPI, there are still potentially some issues because, as I mentioned, the implementations of MPI on the cluster platforms are often quite specialist, and they have specialist libraries and so on. You may find that you can't get the full benefit of the performance that you would get if you build using an implementation such as MPitch. But nonetheless, there are different ways that this can be done. There are different options that you can provide to MPitch. It's got a number of different kind of drivers that can utilize different types of hardware. So there is scope to work around these issues. And in theory, it should be possible to get similar performance, or at least almost equivalent performance, using this approach. The Singularity documentation provides some information on MPI, and it highlights two different models for working with MPI codes. And we're going to look at a model which is the hybrid model. So this is where we actually build our code on a separate platform. So I can build on my laptop or whatever you build on your local desktop, laptop, whatever it is. And we link our code, our MPI code, which has to link against these MPI libraries within that container that we build. And then we take that container over to, within the image that we build, we take that image over to the cluster platform and we run a container from that image. And the code that we've built runs within our container environment using the MPI that's with it in the container, but it also interfaces with the kind of MPI infrastructure on the cluster platform to be able to ensure that the nodes can all talk to each other and the messages can flow between the different processes on different platforms. So that's what we're going to use here. That's the approach we're going to use here. But I know that there are other options. I think there's a bind model, and I think certainly some of the ARCHER2 team, I think, the members who are looking at that approach as well. So there will be documentation, I guess, appearing in due course for that. But just to sort of highlight that there are these different options. So in the remaining time, we're going to have a look at actually building and testing an image with a simple MPI code as an example. So the approach that we're going to use here is that you'll be building your container image on a local platform. So we're going to do exactly the same thing that we did with the simple test image that you saw previously. And we're going to use a different but compatible MPI implementation. So we're going to use MPitch, and that is compatible with the MPI implementation that's on ARCHER2. And we are then going to take that container that we built. We're going to move it to ARCHER2, and we're going to show you how to run that as a parallel job through the queuing system on ARCHER2. So if you're not familiar with large parallel large HPC clusters, this might be a little something that's a bit new to you. They often have these queuing systems where you have to submit your job, and a scheduler will look at the queue and work out how to run the jobs and process them. And we can talk a little bit more about that once we've got the build going. So what we're going to actually run here is something called the OSU micro benchmark software. So it's just a very simple bit of, it's a small scale piece of software that does some benchmarking. So it looks at the performance of communication across different nodes in a cluster. And so what we're going to do is we are going to download the files, the source code for both the OSU micro benchmarks and the Mpi implementation to our local system. And we're going to then create a definition file, which you can see here, which actually builds from source those different bits of software and creates a Singularity image from them. So this is something which, if you had to do this on a local platform, as you'll see, it can be a bit time consuming, and it's also something which is not always the most straightforward thing to do, but we've got it set up here in such a way that it's tested and we know that these builds work, and that should simplify the process for you. So just to get things going, if you want to take a copy of this definition file that's listed here, so what you can do is take a copy of that. So I'll work through the process on my local machine, and we're going to basically do something that's very similar to what we did earlier. But there's a few things that we have to consider here. So the first thing that you'll note is that we have this file section at the top, and in the files section we are taking some files that have the source code for the things we're going to build, and it gets copied into the root directory in the image. So we need to make sure we've got those files sitting in our local directory when we do this run, when we start this. So at the moment we're working in, I've got my Singularity data, it's exactly the same directory I worked in before. There's a whole bunch of other stuff. In fact, that's not the right machine, but there's still Singularity. I'm going to do it on my local machine. So that's right. So here's the Singularity data on my local machine. There's the things that I built before. So what I need to do is I need to get the mpitch and the OSU benchmarks code from their relevant locations. So that's the first thing that we need to do. So what I'm going to do here is I'm going to go to the mpitch downloads page. So you've got the links there for the various different things. I'm going to get 3.4.2, which is the version down here. So let's click on that, and I'm going to save it. And that's going to save off to my downloads directory. And then I'm going to do the same for the OSU micro benchmarks. So you can follow along with me for this. You should be able to get the various different files. Okay, so I'm going to grab that one as well and save that. Okay, and let's go back to this page. So what I've got now, so I'm going to now just move these files from my downloads directory. Oops. Let's move those files to here. So then I'll have them in my local directory. And okay, so I've now got the OSU micro benchmarks and the mpitch source code locally, and I'm now going to get my definition file, which is going to be this here, and let's put that. So let's create a file. So OSU benchmarks.def, and we're going to paste into it this here, and let's save that. Okay, so now we've got our OSU benchmarks definition file, and we've got our source code that we need to use to do the build. I'm going to make one change to the definition file. Sorry, I think we're going to put a question there. Right, so yes, is there any reason why we're using mpitch from source? There is, absolutely. So you can indeed install mpitch from the package repositories, or the Ubuntu package repositories. The problem is that the key here is this line which says with device ch3 nemesis OFI. We're using a specific driver, a network driver, when we build this that will make the performance better on when we move it to the cluster. And the version that's built for the version that's packaged for Ubuntu does not have that set up. It's using a different driver, I think. So that's why we are using a custom build and not taking it directly from the the package repository, which would of course be much easier. I'm going to make one other change here. So to speed things up a little bit. So this depends on how many cores you've got on your machine. But I'm going to change. So this -j is the number of processes that are used when it builds. So -j2 means it will try and use 2 cores or run 2 processes to do the build. I'm going to whack that up to 8 and hope that my machine can handle it and give us a faster build. And I'm going to do the same for the other build for this here. So hopefully that will speed things up a bit. So that depends on how many cores you've got on your machine. This machine actually I think is only a 6-core machine, but should be able to handle slightly more processes. So we'll just see how that works. So okay, so we're now ready to build, and what we're going to do is something that looks effectively like what we saw in the previous. I'm going to go through what's happening there in a minute. But we're going to see something that looks effectively like what we saw previously. So the build command is very similar to what we saw before, but I'm going to have to do the full. I'll do the Docker thing to run it to build it in the Docker container. I'm going to cheat and go back through my my history there. So we've got a command that looks like this: Docker run -it -v to mount the directory. It's privileged. We've got the slim image that we're using, and we're going to say build, and we want to create home singularity osu benchmarks.sif. That's going to be the output, and the file we want to input is home singularity osu benchmarks.def. So we kick that off, and in theory this should work. We'll just wait for a moment to make sure that it's managed to copy in the source files that it needs. Did that work? It seemed to. Okay, so what's actually happened here? Let's just go back to the. So in fact, I'll let that run in the background, and while that's running, I'll just look through the cluster, the image here, to show you what's actually happening. So what's actually happening in this image? So hopefully you maybe have been able to also kick off the build, but while you're either doing that or it's running, I'm just going to walk through what's going on here. Very similar to before, the same starting section. We're going from Ubuntu 2004 Docker image. What does this file section do? So this is new. So what this is saying is take some files that are available and copy them somewhere. So the files that we've got these files in the home directory. So that in that directory in the home singularity directory, which we mapped using -v. And we're copying that into /root because we're going to do the build in that location. So that basically just means that we do the build within the Docker. We're not doing it in a shared directory. And we do the same with this file also. So there's the 2 files that I downloaded originally. I see actually that Michael's put the links in there to wget the files. So that's just saves you going to the website. If you've got wget installed on your machine, you can just type those and pull the files that way. But hopefully by now most of you will have been able to download those anyway. So yeah, so these are the files that we're putting in that are going to give us the initial code. And then we've got these environment variables that we create. So what these are variables that will be available in the environment every time we run a container from this image. So every time we create a new container from the image, we will have a $singularity mpg dir, and we will have a $osu dir available in the shell that we can use. And you'll see why that's useful in a minute. And then we've got our post section, which is the same as what we had before, but there's rather more going on here than before. So we install a bunch of packages. So you can see that we do update our package directory. We then go off. We've got this Debian front-end non-interactive. That just avoids some large quantities of messages that come up because we're running in a non-interactive environment. Otherwise, it prints up a lot of messages in the install process to do with some of the packages that are being installed. And we're installing some particular things here. We're installing Build Essential, which gives us a whole set of compilers that are required for doing standard software builds. These libfabric and libIb verbs are to do with the networking device that we're going to build with mpitch. So we need those libraries. And then G4tran is a Fortran compiler because there's some code within, I think within mpitch that's Fortran based. So we need a Fortran compiler for that. So we then go off into the root directory. Why do we go into root? Well, that's where we placed our files. So here we copied the files into the root directory. So that's where we're working for the build. So we go into the root directory, we unzip the, sorry, I'm in the wrong section, it's here. We go into the root directory, we unzip the mpitch code, we change into the directory, and we do the configure. If you're not familiar with building code from source on Linux, it's a pretty standard approach is to run the configure to start with. Then you do make, which does the actual build. As you saw, I increased the number there to build on some more processes to try and speed things up a bit. And then you do make install, which will install the code into the system at the sort of standard system paths. And then we do the same for the micro benchmarks. So we basically unzip it, we go into the directory, we run a configure, we tell it which the MPI compilers are to use, and we do the make and make install. And right at the end, we have our run script. And what does the run script say? It tells us to run something from OSU-dir. And then this $* basically takes all of the additional parameters that we put on the command line and drops them onto the end here. And you'll see in a minute that we use that basically to run the commands. There's a whole suite of little tools that are in this OSU benchmarks, and they all live at the base directory OSU-dir. So we always want to run something which is in OSU-dir, but we then want to add on to it the name of the tool we're running. So we'll see that in a minute. Okay, so at that point, we've got our thing that's building, and what we're going to want to do in a minute is to run one of the tests when it's built. So we're just going to have a look how this is getting on. So you can see here, there's loads and loads of output coming from this. This is all of the mpitch building. It's a very large package, and it's going to run through for a little while, but I'm hoping it should be finished pretty soon. Do we have any questions at this stage? So somebody asks, why isn't there any output? I think there's somebody answered that. Somebody's asking why isn't there any output from the following command: Singularity shell ---- contain, but the same image in command group Singularity. Right, I think that's a good question. I suspect that's because you've presumably got an alias set up for Singularity on your local system, and I suspect you may not have put the -it flag in the alias. So what's happening is it's basically, because there's no interactive terminal being created, it just starts the container and then exits. Whereas when you run on ARCHER2, because you're running directly on a system with an install of Singularity, and you're not running in a separate container, it runs fine. So I think probably if you look at your alias on the local machine, you might be missing the -it from the alias command, and that probably would explain why you are not getting things working locally. Hopefully that solves the problem. Okay, so there's another thing there with an error. What do we see there? Permission denied. Right, okay, so in fact, it looks like people have actually been able to get to the point where you've either got the image running or you're using the version that was on ARCHER2. And right, okay, yes, great, glad that's sorted. Yeah, so that's basically the errors that people are talking about there are things that we're coming to now. So there's also, yes, once you've got this thing going at the end, the files get rather large, and it might be a little bit time consuming to transfer it. So we will actually move across and use the version that's on ARCHER2 to test with. So my thing is running here, and what I'll do now is I'll switch across to Archer, and I think we have our Singularity. I've got to remember there is a EPCC Singularity directory is the one I'm thinking of. There it is. Right, so there we have the OSU benchmarks.cif file. And so what I'll do is where am I here? I'm just going to copy that across. I don't actually even need to copy it across. I can just use it directly from there. But I think for the purpose of this, I will copy it. So let's just CP that to here. Okay, so what we can actually do here is if we say Singularity, just to test locally, what I'll do is I'll create a Singularity shell in the OSU benchmarks.cif image. Okay, and what I can see now is that I should find that at the directory, do we have OSU dir? No, we don't on this one. So the OSU dir on the version that's on ARCHER2 does not have the OSU dir variable set up, so you have to use the directory, the full path to the folder. So I'm looking in here. You can see that this is the OSU benchmarks that are built inside the image. The startup directory has a simple little OSU hello thing in it. So what I'm going to do is run that, and I think I probably have to use MPI run. So I'm going to do MPI run. So MPI run is the thing that you use to run an MPI code. So it's a kind of wrapper that handles the process of setting up the MPI environment. So I'm just running locally within the Singularity container here on ARCHER2 as a test, and I'm only going to run one process. So minus NP is number of processes. We just want to run one, and we're going to run OSU hello. What we should see is that that actually runs, and it tells us it was a test with one process. So hopefully, if you actually manage to get the thing built, that's great. And maybe you have, well, if you're still copying it over, if you have managed to copy it to ARCHER2, you might find that you can actually open a terminal using Singularity shell with your image, and then try and run the OSU hello. If you're taking the version that I copied, so there's people are concerned about uploading. I do understand if it's a problem. Yes, there is a version that you can use. It's the one that I just copied. So if you want to copy the version that's on Archer as a sort of the one that we made earlier, if you look in $EPCC Singularity dir, in fact, it keeps replacing it for me, but it's basically EPCC Singularity. Whoops. Yeah, so I think that's the directory that you want, and there's an OSU benchmarks.sif in there you can copy on the ARCHER2 platform to play around with, rather than waiting for the whole thing to build and then having to upload it. Okay, so we've now got our image here, and I've shown how I can go into a terminal and run OSU hello, but what I actually want to do now is to run this in parallel on the platform across a number of compute nodes. And so what we've done to make that easier for you, so ARCHER2 uses a system called Slurm as its scheduling system, its workload manager for running parallel, for running large-scale HPC codes. And this is the system which we use to basically queue up our jobs and have them run on the ARCHER2 platform. So in order to work with Slurm, we have to create a job submission script. So this is a script that Slurm will interpret to understand the parameters of our job and understand what resources we need and so on. And it will then schedule our job onto a queue and will manage the process of getting the job run on the compute nodes. So on a large HPC platform, if you're not familiar with these things, what you generally have is your kind of interactive login node. So this is the node that we're on at the moment. But then behind that, you've got some number of other compute nodes that are sort of sitting there waiting to run tasks, which you never actually log into yourself. They're not available to you to log into. They're kind of hidden in the system. But the workload manager system will actually handle the process of actually dealing with pushing the jobs out onto those compute nodes and running. So in view of time, I know we're pretty limited on time. What we're going to do is just look at this example of how to actually run things. So you can have a go at running this particular example with the local one. I'm glad to see some people are actually managing to get stuff running. And you can actually run, there's another sort of example there that you can do a two process run using the OSU latency. But we want to look at actually doing a parallel run. So what we're going to do is we're going to use a template script that we've provided. So if I look at that template script, so let me just save that. So what I'll do is I'll just copy that from, so actually that's on ARCHER2, that's not very helpful, but I'll copy here. So in fact, my image is built, how big is my image? 230 megs. So what I'll do is I will just have a look at the Slurm script, which was, I think, what was the name of the file that we had? It was OSU latency. I'm getting confused here, maybe. Oh, that's what's going on. OSU latency. So that's the thing. While that's actually going, I'm also going to just start the copy of this. We'll see if it copies in time it might go reasonably quickly. I'll just kick that off, and then I can go and look at the script and show you what's going on there. So let's just copy that to ARCHER2. So that will kick off the copy, and we'll just see how that goes. So here is our job script. It's a kind of template. You can take the template and you can copy it and then edit it yourself. There's a lot of options in there that you can see that have been pre-configured for you by the ARCHER2 team. You don't need to worry about what most of them mean. There are just a few that are of particular importance. And what I'll do is I'll just go to my ARCHER2 terminal, and I will create a Slurm script, and I will paste in the contents of that, and I'll just quickly walk through the bits that need to change. So the things here are these sbatch directives at the top. So these are things where you set up your job name. So I'm going to call it OSU test username. How many nodes you're going to run on, and how many tasks per node. So here we're actually going to run 128 processes on each node. So we're doing it across 2 nodes, and there's going to be 128 processes on each. Number of CPUs per task set as 1. This is all kind of the default settings that were there. We're using the standard quality of service. This will put it into a certain set of queues, and I believe that we've got some queue priority for this course, so we should find that it runs pretty quickly. And then we need to put in our code. I believe it's TA032. I'm sure Andy will correct me if I'm wrong there, but I think that's the right one. And I think that's everything that we need to change. What we then need to do is to actually set up what we're going to run. So where things are going to run from. So this is going to run the OSU benchmarks.cif. It's going to run collective OSU all reduce. And I need to run this in a work directory. I can't run this from my home directory. So I don't know if I need to put the absolute path. I'm guessing probably not. So we'll assume that that's okay like that.
So no, Slurm's happy with it as long as you submit it from the directory
Right.
that the OSU benchmark.cif files in. That's fine. Or you could use the centrally installed version by just putting the $EPCC Singularity dir environment variable.
Oh, fine. Okay. Right. Okay, that's great. Right. So I'm going to go into my directory in /work. So each of you should have a directory that's in /work TA032 TA032 and then your username. So I'm going to go into there. So in fact, what I'll do is I'll just copy my OSU benchmarks files to there. And then I'm going to go into that location and okay. Right, and what I'm going to do now is I've got my Slurm script there. And what we can see is that it's telling it, I've told it the various different things. I've told it who my user is. I've said it's got a limit of 10 minutes because it's going to run very quickly. Various other configurations. And what it's going to run, it's going to use the srun command, which is part of the Slurm batch job submission process. And it's then going to call Singularity run with some options that are all the options that are here that are specific to pointing the right directories for the networking to the system. Singularity run the benchmarks, OSU benchmarks.cif, and then this collective OSU all reduce, which is the benchmark we want to run. And what we can then use is the sbatch command to submit that. What that says is take this script that we've got with all of this configuration in it and submit it to the Slurm submission system or to the Slurm management system and let it run the job for us. So I run that. It tells me that the batch job is submitted. And what we should now find is that the job, I don't know if it will have run already, but we can have a look. Something is happening already. So we can actually look at, maybe it's even run already, has it? Looks like it might have already run. So if we look at that file, slurm419688.out, and I'm using ls-alrt so that shows me the files in date time order, so I can see the most recent one at the bottom, and I can see that that's just been created. And if I actually look at the contents of that file, sure enough, it hasn't actually run. And so normally it would print out these rank messages with the rank number, but on this particular platform, the value that I'm using to print the rank isn't working. But it does show us that there's basically been, however many, is 256 processes that have run here. And they've all been communicating with each other, and then the benchmark is looking at the time for sending different amounts of data between all these different processes. And it's telling us basically how many microseconds it took to send data of these data blocks of different sizes, or data messages of different sizes, between the various, or gathering them across various numbers of processes. So while it's not important to really understand what it's doing, the point is what we've actually achieved there is we've actually been able to run a parallel job in a Singularity container, and to be able to run that on ARCHER2 across the various compute nodes. And if this is something you're interested to be able to do with your own jobs, then this hopefully gives you a nice kind of template to work from, the approach that we've used here. I appreciate it's been fairly quick going through this section of the material. There's a bit more discussion there that you could read through if you would like to, but hopefully that gives you that illustration of kind of how this process works. And I think, you know, this, I didn't want to dwell for too long on this section of the material, because I know this is something that may not be hugely relevant to everybody, but certainly for those of you that are working with large scientific codes, it may well be something that you need to do.
Jeremy, one useful thing to note for people
is
go ahead. Your ARCHER2 access isn't just going to finish at the end of today when the course finishes. It's still going to be available for a few weeks afterwards, at least 3 or 4 weeks afterwards, after the course finishes. So you can still log on and use ARCHER2 to run tests and to try out these sort of things if you want to have a go at that sort of stuff and use Singularity on ARCHER2. So you won't lose your access at the end of this, at the end of today.
That's great. Yeah, thank you for that. Okay, so what I can actually just do as well here, sorry, just very quickly, is to show you that. So this is the image that I just built on my local machine and copied across. The copy is finished. So just to wrap up, I will copy that into the same location as the one that we ran here. And I'm going to copy it to OSU benchmarks new. So this is my new image. And I will just edit the Slurm script just to prove to you that it should work, what we've just built. So you can see that, so let's edit OSU benchmarks.slurm. And I'm going to tell it to run the image, the new image that I've just copied across. Okay. And just S-patch that. So some of you may or may not have got to this point, but hopefully this will show you that what we built locally and then copied across, I hope, will work. So there's the job number that we can see. So in fact, the output files have the job number appended to the end. So let's have a look. So that will take a minute probably to run. It hasn't run yet. Hopefully it's not going to fail. We shall see. There's something happening already. We've got an empty output file, so it's been scheduled and it started to run. So I have to say that if you're not familiar with these platforms, it's fairly unusual for things to run quite so quickly. If you've got a large job that wants lots of processors, you may have to wait in a queue for some period of time. It just depends on how busy the platform is and what's going on. But in this case, it's been set up such that we have for the course something which runs in a decent amount of time. So in fact, it appears to, we've got the same size output file as before, so it appears to have completed. And we can have a look at that, and we can see that we've got some output there. I guess the timings are very similar to the previous one, are they? Hang on, I don't know. They probably are. Let's have a look at the previous one. Tail that, the last 20 lines. Yeah, so there's a slight difference. So it ran, I mean, probably we're talking about sort of tiny timings. We can see that they're all, that one was 882 microseconds, that one was 897, but then this one is slightly slower. So we can see there's a slight variation, but we can indeed see that the image that I built locally on my machine using that script in the material is working. So, as I say, we've gone through this very, very quickly, but I equally didn't want to spend a huge amount of time if there are people who were sort of less interested in this and more keen to see the general stuff. This concludes these 8 episodes of the Singularity material. I hope that you found this useful, particularly as a kind of an alternative way of running containers to what you saw yesterday with Docker. And I hope that you also found the ability to use Docker, building on the knowledge that you gained with Docker yesterday, to actually run the Singularity build process, gave you an example of both the flexibility of Docker, but also being able to actually use it for real. So yes, I hope that was something that you found interesting. This material, as I say, is developing all the time. We're always keen to have suggestions on how we can improve it. We had a really good suggestion about using the workdir switch earlier, so I'm going to look at that. But certainly happy to receive any comments. I know some of you might need to dash off, so that's why I'm going to wrap that up there, but I'm happy to stick around for a little while longer. So if you want to still have a go at getting these things to work, or you want a bit of time to play around with things, you're very welcome to stick around, ask questions, and if you want to kind of get to the end of the section of the material, then please do feel free to stay around and work on this. And as Andy pointed out, you will also still have access for a bit to Archer. So if you want to try this another day, you're welcome to do so.
The only other thing I want to say before people just disappear is that I posted a feedback form in the chat, which you please fill in. I know there were some comments in the end there about pacing and stuff like that. We'd love to have them because we always want to improve things. Also, you'll get an email reminder about filling the feedback from our training organizer as well, which will have the link in. So if you don't get it from the chat there, you'll get it via email as well. But please, even if it's just a short time you take to do some feedback, it's really important to us.
Great. Yes. Okay. Thanks for that, Andy. Please do, as Andy says, please do fill in the feedback because it's really useful for us. You know, anything, both things that you think are great and things that you think could be improved. We're always very happy to hear either way because it will help us to improve things. So with that, I will kind of officially close the session for today. And as I say, please do stay around. I'm happy to stick around for a while. And if you've got questions that you want to get addressed that you haven't yet been able to address, then we're happy to do that. So thank you all very much.